Hi, I'm 𝗦𝗲𝘀𝗀𝗶cie, and I'm a program manager on the Azure Cosmos DB team. I'm joined today by Ayush Kataria, who's a software engineer also working on Cosmos DB. We're excited to talk to you today about designing reliable multi-agent apps with Azure Cosmos DB. And the example that we'll use today is a travel assistant, which is a multi-agent AI application that helps you plan personalized trips. One of the functionalities of our application is a chat feature. When a user wants to plan a trip, they can start a chat by saying something like, "Plan a trip to Paris." This first gets routed to our orchestrator agent, who then can pass the message to various specialist agents, like the hotel agent. We can look up memories in Azure Cosmos DB with context that we already have stored about this user. We can embed the initial query with Azure OpenAI so that we can turn it into vectors that we can then search against our existing other metadata, like places and restaurants and hotels in Paris that may be useful for our user. Then we're ready to send our message back with the data that we found and help them plan their trip. This is just an example of one turn. And if we look at the user interaction flow, we can see many pieces of data that are moving through this user journey, from the message to the various agents we're talking to, when we're ready to actually create the trip. And lastly, we need to extract the memories so that we can remember what's happened next time the user comes and logs into our website. There's various things that we want to focus on in different parts of the user flow that will really help us keep the best user experience. In the beginning, the latency and personalization is the most important. We want to make sure the agent remembers key things about our users and that the responses are very fast. Otherwise, the user may become frustrated and they may go to one of our competitor travel sites. Whereas in the back half, consistency and reliability become more important. We don't want to accidentally double book a trip or forget something that we already talked about. So really keeping in mind the user perspective as we build our application will help us ensure that our application is reliable. Now, I want to zoom in on one thing, which is the number of agents here. We've talked about an orchestrator and some specialists. I want to hand it off to Ayush, who's going to talk more about the multi-agent pattern and how it can help us in our application.
Thanks, Justine. Going over the travel scenario that we'll be discussing today. Hi, I'm Ayush Kataria. I'm a software engineer at Azure Cosmos DB. So let's dive into why multi-agent. So let's start with what goes wrong when you don't. So on the left, you see the single agent problem. When you have one agent trying to handle every domain, all packed into a single system prompt, the model gets confused. It doesn't know which capability to invoke or when. There's no separation of concerns, so every change risk breaking something else. You can't scale or improve any area of expertise without touching everything. And as conversations grow longer, you hit context window limits, the model starts forgetting earlier parts of the conversation, leading to inconsistent behavior. So on the right-hand side, we have the multi-agent solution. Instead of one monolithic agent, you have specialized agents, each with a focused prompt and a specific set of tools. So an orchestrator sits on top, routes the user's request to the right specialist based on the intent. So this gives us a few big wins. So first, each agent has a smaller, more focused context, so it reasons better. Second, you can develop and update agents independently. Adding a new specialist doesn't require touching existing ones. Third, it's composable. You can plug in new capabilities without rewriting the whole system. So now let's look at how agentic memory works better than retrieval augmented generation. So this is where we get into, I think, which is the most interesting part of this talk, that is agentic memory. So most people are familiar with RAG, that's retrieval augmented generation. You have a knowledge base, you embed documents, and when a user asks a question, you retrieve the relevant chunks and feed them to the model. So it works well for what it does, but has fundamental limitations when you're building agent-based applications. So let's walk through the comparison. Traditional RAG is static. Your knowledge base is fixed until you explicitly update it. Agentic memory, on the other hand, is dynamic. It grows automatically with every interaction. RAG gives the same results to everyone. It's searching a shared corpus. Agentic memory is user specific. It stores individual preferences and history, so two different users get completely different experiences. RAG retrieves by similarity alone. Whatever is closest in the embedding space comes back. Agentic memory uses salient scoring, which factors in importance, confidence, and recency. RAG doesn't learn from interactions, it's just a pure lookup. Agentic memory actively learns and adapts. Every conversation is an opportunity to extract new knowledge. And RAG has no concept of time. Agentic memory supports cross session persistence with TTL policies. Let's now go over the system architecture for our travel agent application that we are going to demo at the later end of the session. So now let's zoom out and look at the full system architecture. So everything starts when a message lands in the orchestrator agent. This is the front door of our application. So every conversation comes through the orchestrator first. Its only job is to understand intent and decide which specialist should handle it. After that, there are specialized agents, hotel, dining, and activity. Each one owns a single domain, so has its own system prompt and pulls from a focused set of tools. In our multi-agent application, none of these agents are talking directly to the database. They go through the MCP server, which has many tools like recall memories, discover places, transfer between different agents, and many more. The point of MCP is decoupling. So we can update or add tools without touching agent code. And one tool can be reused across every other agent. So underneath the MCP layer, we have our Azure Cosmos DB. It stores everything the application needs: sessions, messages, places, trips, API events, among others. Places are searched using hybrid search, and every container uses a hierarchical partition key, so the system is multi-tenant from day one. Next, we have the Agent Memory Toolkit, which is a new Cosmos DB offering to host your memory layer. So for any multi-agent application, it is a separate background runtime that hangs off the same Cosmos DB account that I mentioned before. It owns its own container called memories, where the actual turns of the conversation, facts extracted from those turns, the user summaries, the thread summaries, everything is stored. And the agent never calls it directly. And then we have the Azure OpenAI which is providing the LLM reasoning and embedding capabilities. It's a shared utility that feeds both the agent runtime and the toolkit pipeline. Now let's go over some concepts about memory and agentic memory. So before we go deeper into memory, let's establish a clear vocabulary. People use the word memory loosely, so let's be precise. So there are three distinct concepts here. State, which is the snapshot of your entire application at any given moment. It contains everything needed to restore the application to that exact point: what the user said, what the agent decided, what tools were called. Then we have short-term memory, which is what happens within that particular single session. It's the conversation history, the messages going back and forth. This is what lets an agent refer back to something the user said 3 messages ago and give a coherent response. Then we have the long-term memory. This is where things actually start to get more powerful. This persists across sessions. When a user comes back days or weeks later, the agent can recall what it learned about them previously, their preferences, past decisions, feedback. And this is what enables personalization and learning over time. It's the difference between an agent that starts fresh every conversation and one that builds a relationship with the user.
So, Ayush, these are really interesting different types of memory. I'm wondering, how can we implement these into our travel application?
Yeah. So in our travel application, we are going to implement all three of these different kind of memories. State management through LangGraph's Cosmos DB checkpointer integration, and then short-term memory and long-term memory through the dedicated agent memory toolkit backed by a Cosmos DB. Now let's move over to the code, and I'll go over a few more core concepts, and then we can jump into our UI demo and look and get the feel how the agent memory toolkit works with our multi-agent application. So we just talked about long-term memory at a high level. Now I want to break that down because not all long-term memories are the same. And the toolkit reflects that with 4 different types of memories. So the reason this matters is each type has a different lifetime, a different way of being created, and a different way the agent uses it. So let's walk through them. As you can see here, we have a few different types of memory that we are storing in our agent memory toolkit. First is the facts. So it's sometimes called semantic memory. These are simple, durable statements about the user. User is vegetarian, travels with a wheelchair, lives in Seattle. They are objectively true, they don't change often, and they should never expire. Second is the procedural memory. This is behavioral patterns, preferences inferred from how the user actually behaves over multiple conversations, tends to book boutique hotels over chains, prefers late dinners. These are softer than facts, so the user might never say them out loud, but they emerge from repetition. They also never expire by default because behavioral patterns are usually stable. Third is episodic memory. These are tied to a specific time and place. Visited New York City in last spring, loved seafood on my Barcelona trip. These are how the system knows to reference a past trip when planning a new one. And these do expire. So the default is 90 days. Episodic memory gets a little noisy too fast, and a recommendation system doesn't really need to remember a coffee shop that you went probably 4 years ago. Fourth is the user summary. This is different from the other three. It's not extracted from a single message. It's a rolling synthesis of who this user is, regenerated automatically every few turns. It can be something like this user is a frequent solo traveler, vegetarian, prefers cultural over outdoor, mid-range budget hotels. So the orchestrator pulls these into its system prompt at the start of every conversation. So even on day one of a brand new session, the agent already knows the user. So let's go and look how it looks in the UI. So let me sign in with a user Tony, for which we already have some preferences loaded. So let me go talk with the chat assistant. Let's say, hi, I am planning a trip to Tokyo. And you'd be able to see that it's actually in the logs where my API server is running, that it's actually going to the orchestrator. Orchestrator then works its magic, figure out what's the intent of the particular user, what tools would I be using, where should I go, and then eventually it gives us a response that, hello, to get started with Tokyo trip planning, please let me know what hotels you want, what activities you want to do. So let's see, let's ask it, what are my hotel preferences? And if we'll actually head back to the portal, we can actually, for that particular user in our memories container, I can search what all facts are actually stored. So if I'll execute this query, I can see the user's name is Tony. Tony prefers luxury 5-star hotels. He loves art museums and contemporary galleries and everything. So if we'll head back to our UI, I can actually see that based on your past interactions, here's what I know about your hotel preferences. You prioritize reliable Wi-Fi over price for business trips. You enjoy rooftop bars and quiet evenings during work travel. So similarly, I would be able to fetch my preferences for activities, my preferences for restaurants, my dietary preferences. So that way, the agent toolkit is extracting the memories, storing those preferences back in Cosmos DB. And when the user is coming and actually chatting with the chat assistant, it's able to leverage those preferences and memories back into the conversation. Now let's head back to the code once more and let's see how are we actually extracting all these memories. So storing memories is only half the challenge. The real value comes from making all this memory intelligent, meaning the system actively manages its own knowledge. So if we'll go to this particular class, we have public ape-facing APIs, which are extracting memories, generating thread summary, generating user summary, and reconciling memories, which means conflict resolution. So the first piece is the threshold-driven extraction, which is extract memories. So the real value comes from making memories intelligent. So the user never has to say, remember this. As the conversation unfolds, a background pipeline runs every nth turn in the agent memory toolkit and asks the LLM, is there anything new about this user worth remembering? If the answer is yes, it pulls out a fact, classifies it as a fact, procedural, or episodic memory, and writes it back to Cosmos DB. The agent loop doesn't wait on this, it happens asynchronously in the background. The second piece is conflict resolution, which is done by the reconcile memories method. So real conversations always would be contradicting. The user says, I'm vegan on Monday. 3 weeks later, they mention how much they love a steakhouse and they have started eating meat. So now what does the system do? So on a separate cadence, the toolkit periodically sweeps the user's facts and asks the LLM to classify the pairs of related memories. So they can be either duplicates or updates. When it finds one, it doesn't delete the user, it marks it superseded by the winner. That is done so that the audit trail is preserved. So the user never sees a contradiction in the recommendations. But if you're debugging, say 6 months later, you can still see exactly when and why the system changed its mind. The third place is rolling summaries. Conversations can get long. Token budgets are finite. The toolkit handles this by generating two kinds of summaries on a cadence. So one is thread summary that captures the current conversation, the current session in the thread. And other is user summary that captures who this user is across all conversations. So just for this demo purposes, both user summary and thread summary are regenerated after every 5 turns. So we can actually see that happen in the demo in a few minutes. In production, the agent toolkit has like some defaults set which are tunable by the customer who's going to use the agent memory toolkit. So the orchestrator eventually pulls these summaries into context at the start of every turn. So even after 100 messages, the agent doesn't lose the actual plot. The fourth piece is what I think of as the payoff, that is memory condition search. So everything that we've talked about so far is plumbing. This is where the memory shapes what the user actually sees. So before any specialist agent searches for a hotel or a restaurant, it recalls memories first to ask the toolkit, what do we know about this user that's relevant to this particular query? So the recall comes back with relevant facts and preferences, and the agent then encodes those as explicit filters on the search call. That's how show me hotels in Tokyo silently becomes show me luxury hotels in Tokyo. So the personalization isn't bolted on at the end, it's baked into the query itself. So the agent memory toolkit runs all these automatically in the background on the right cadence without the application code having to coordinate them. And your agent always stays simple. So now let's go back to the UI and let's see how we'll choose a new user that has no preferences stored in our memories container. So let's see how the workflow is. So let me close this. Let me log out of this session. Let's choose a new user as Peter. And we can go in our portal, we can confirm that Peter doesn't have anything stored in the memories container. Let's go back here. Let's start a session. Let's say I'm planning a trip to Paris. Similarly, again, now if I'll go to my API server backend in the terminal where it's running, I can see now the user chosen as Peter. It's going to the orchestrator agent and like other tools that the orchestrator agent decides to go to. Let's head back to our UI. I have an answer. So hello, I'd be happy to help you plan your trip to Paris. Would you like to start by finding hotels, restaurants, or activities, or perhaps create an itinerary? So let's say I am vegan. Now if you'll head back to the portal, you can actually see some memories stored for that particular user. So this is a memory type turn. Turn is nothing but just the conversation that the user and the agent is doing on our chat assistant. So as we said, I'm planning a trip to Paris that is stored as a turn. Then right now it's storing I'm vegan as a turn as well. If I'll execute the query again, you can see that it was able to extract the fact that the user is actually in fact vegan. So let me go back to the UI and let me deliberately contradict myself. And let's say I have started eating meat. Now, again, if I go back to my portal, let me now filter it for just facts so that we can see how the fact is getting resolved. So right now we only have one fact here that the user is vegan. Let me execute the query again. So now you can see we have a new fact that the user has started eating meat and changing from a vegan diet. And if we go to the older fact that was the user is vegan, I can see that it's superseded by the same fact ID of my new fact. So that is done for an audit trail. As I explained before, if after 6 months or a year down the road, you want to check like which fact was superseded by which fact, we would have a debug log in that sense. Let's head back to the UI. Just a couple of other things that I wanted to mention is that the prompt for these LLM models are scripts that are written in our code itself. So if we'll go back to our code and I can show you like an extract memories prompt file. So here you can see that we are deliberately giving instructions to the LLM that these are the 4 different type of memories that you can extract. And we have given like detailed information in the prompt, like what should be the structure of those memories, rules according to like which rules and examples that what kind of a memory would be classified as fact, what would be classified as procedural, what would be classified as episodic. And similarly, prompts have been given there are rules given to this prompt that what kind of turn should be extracted. So for an example, if my turn just has greetings to the assistant, those turns would not be extracted as a fact. So if I'm just saying hello, hi, good morning, good afternoon, so those turns would not be extracted. Now let's look at how auto summarization works. So as I mentioned, just for this demo, we have set that cadence as 5 turns. So as soon as there would be 5 turns, auto summarization would be generated. So let me ask it to recommend me some restaurants now. So now if we'll go back to our terminal window, I would be able to see that the orchestrator agent actually extracted the intent, and it was able to call the dining agent to actually list the recommendations for restaurants. So let's go back to the UI and see what all results we get. So you can clearly see that it says that here are some restaurants recommendations in Paris and based on your updated dietary preference. So it's automatically picking up the current fact that we have in our memories container, as we have already resolved that conflict, and it's able to give us the correct recommended list of restaurants. Now, let's say we can say create an itinerary for Paris for 3 days. And as we can see, we have already done 5 turns with the agent. So we can actually go in our portal and also see if a summary is being extracted. So we can see that a user summary was extracted. If I'll run the query again, we should be able to see. Yeah. So we can see the user summary. The user is planning a trip to Paris. The user has changed their dietary preference from vegan to omnivore. So similarly, we would have a thread summary that would be extracted as well. And we can also see here that the itinerary agent was able to generate the whole itinerary for us. So the agent memory toolkit for Azure Cosmos DB is in public preview now. It has fact extraction, auto summarization, and there are package instructions and prompts to do conflict resolution, extract different kind of memories, do user and thread summarization. Next, LangChain Azure Cosmos DB integration is also generally available. It's a integration package that has all the Cosmos DB integration for LangChain and LangGraph that were used to build that multi-agent application. You can use the vector store integration from LangChain. If you want to do state checkpointing for your multi-agent application, you can use the LangGraph checkpointer store.
So, Ayush, it looks like we've implemented the memory toolkit and LangChain, and there's a lot of touch points with Cosmos DB in many different containers. How can we verify that we're following all of the Cosmos DB best practices in this application?
That's a really great question, Justine. So let me set up the scene. So most of the AI apps I've been building lately work. They pass the demos, they look great in a notebook, but there's a gap between it runs and it runs at scale without setting money on fire. So in Cosmos DB, that gap is paved with decisions that you make on day 1 and pay for on day 90. That the partition keys you didn't think hard enough about, the indexing policy you left on defaults, the document shape that looked clean in code but blows up your RU build in production. So that's why we are introducing a Cosmos DB agent kit. So I'll show you. So you just need this one line of code that can just install your agent kit. And it would install these agents. You would have different skills that would have Cosmos DB best practices. Now let's go and see it in action. So I can just ask it that, can you provide me some recommendations on best practices for my data model. So what's happening behind this prompt is the important part. So the agent kit isn't just a service. It isn't an account you provision. It's a repo of skills that any agent skills compatible coding agent can pull in, like GitHub Copilot, Claude Code, Gemini CLI, and others. And what these skills do is they give the agent Cosmos DB instincts of someone who has been shipping on it for years. So partitioning, indexing, RU economics, modeling for actual access patterns instead of how the data feels in your head. So here's the report ranked by impact, highest ROI first. So let's just go over the report. So it's giving you some critical recommendations. It's giving you some really highly important recommendations. And you can also interact with the agent if you want to push back on something, and you can tell the agent that why did you did something in a certain way. So it can be an interactive, collaborative effort with with this particular agent. So who is this for? So if you're new to Cosmos DB, the cognitive tax of am I modeling this right basically goes away. So you write code, the agent kit reviews it, and you ship something that's well architected by default. So if you're a seasoned Cosmos DB developer, point it at your existing services and let it hunt for the things that have quietly been costing you. So like old containers with stale index policies, queries that grew teeth over time, partition keys that stopped aging well. And the part that genuinely changes how teams operate is you can drop this into your CI and your PR reviews. Now, every change gets a Cosmos DB expert opinion before it merges. So automatically every time at no extra cost. So that's the leverage of using the Cosmos DB agent kit. This Cosmos DB agent kit is generally available now.
Awesome. Thanks, Ayush. Now we can feel confident that we have all the best practices in place for partitioning and cost management. But I also want to make sure we're production ready and that we're using all the best practices for reliability and availability. And really, before we analyze how to do that, it's important to go back to the user requirements and what we need to guarantee to our users in terms of three key metrics. The first metric is SLO, which is the target level of service availability. Now, we have a global application, and we want to make sure that our application is always available for our users that may be chatting from all over the world at any time of day. So we really can't have any downtime in our application. And we also want to look at two metrics for RPO, recovery point objective, and RTO, recovery time objective. Now, for distributed cloud applications, it's not a matter of if a disaster will strike, but when, and to ensure that we're prepared when something happens. So for recovery point objective, we need to define how long before the disaster strikes could we potentially lose data and ensure that our application has RPO targets that meet our user needs. Now, after the disaster, there's a potential time of downtime. So how long is it acceptable for us to be down? In our application, we really want 5 nines of availability. We want our application to be always up, and we want it to be available in all around the world. So we can use the active-active pattern in Azure Cosmos DB to ensure that we're getting those 5 nines of availability. Now, in Cosmos DB, there's 2 different ways to achieve the active-active pattern. The first is with the multi-writer. In the multi-writer, you have multiple Azure Cosmos DB regions, and they're all simultaneously accepting both read and write traffic. This is leaderless, meaning writes can come into any region, and they're conflict resolved across all regions. In this setup, the RTO is 0 because all regions are already online and ready to accept traffic. The RPO is effectively 0. It's basically the conflict resolution and the replication time across regions. Now, in the single writer setup, This is enabled by a new feature called per-partition automatic failover. This allows us to failover at the individual partition level. Rather than waiting for an entire region to become unavailable and failover after that happens, we're able to react in a much more agile way by responding at the partition level. This is when you think about a brownout versus a blackout. It's much less common for an entire region to go down than an individual partition to maybe experience failures that require failing over to a new region. With per-partition automatic failover, the unaffected healthy regions or partitions are still reading and writing from that primary write region, where any partition that is experiencing issues can fail over seamlessly. The application handles all of this, so we don't need to coordinate the failures in our app side, and we don't need to make an expensive call on when to fail over the entire region. So this gives us the active-active pattern with 5 nines of availability without actually having multiple writers. Per-partition automatic failover is now generally available. This gives us 0 downtime, 0 data loss, and with 0 touch, because the SDK does the heavy lifting for us. So now we know that we have availability at the partition level, but we still do need to manage some complex operations in our application on the write path. Even though our writes are guaranteed to be available because Cosmos DB will be up, we need to make sure we still have consistency. Imagine the scenario: our user has planned the trip with our travel app and they're ready to book. So when they say book it, 3 things are really happening independently. First, in our trips container, we're updating the status of this trip to booked. We need to store memory. We need to remember next time the user goes to chat with our app, they need to remember that they actually booked a trip to Paris. And lastly, in the events container, we need to emit that booking event so that our downstream systems and our logging also are coordinated with this write. Now, in our application, we can manage all of these independently, but they are writes to separate containers. So what if one of them fails? This is a really bad user experience. We don't want the agent to forget that a user actually booked a trip. We can use distributed transactions in Cosmos DB, which is now in public preview. This gives us atomic execution of multiple requests, whereas previously you could have a transaction within a single partition key. Now you can get atomic transactions across partitions or even across containers, like we have in our use case. This means all 3 of those operations can either succeed or fail together. This gives us consistency at the container level and also simplifies our application, which improves reliability. We no longer need to manage all that error handling in our application, and we can let the platform do the heavy lifting for us. If you remember our integrated embeddings in our embeddings generation, this is another opportunity to let the platform do the heavy lifting. The current flow that we have today is our natural language chat. So our user is giving a prompt. Before our application can do anything with Cosmos DB, we need to call OpenAI and we need to generate those embeddings. This leaves room for potentially rate limiting or error handling. It's more coordination that needs to happen in our application, where we could see write loss availability without Cosmos DB actually being down. Maybe it's an issue with our error handling. And this makes it really brittle for the application, and it puts the heavy onus on the developer to make sure that all of this is going smoothly. With integrated embeddings, this flow simplifies. So we no longer need to have that external synchronous call to OpenAI before we can keep going in our conversation. We can use integrated embeddings to write the raw message into Cosmos DB, and it's automatically integrated with Microsoft Foundry. The embeddings are generated asynchronously, and this allows us to focus on our business logic instead of focusing on coordinating all of these external calls. Integrated embeddings automatically generate the embeddings at write time. You define your Microsoft Foundry integration, and you no longer need to rely on external pipelines to do all the plumbing for you. You can define the source and the target properties to create these embeddings on, which really gives you the full control for how the embeddings are generated in your application without needing to worry about coordinating that in the app itself.
Integrated embedding seems to be such a great feature, Justine. Like while building my multi-agent application, while I was testing it, chatting with the assistant, I was getting rate limited so many times, and I had to wait for sometimes even for 30, 40 seconds to get actually the message back from the LLM. That sounds really nice. I was just going through my trips container and I actually thought of another scenario that I have a lot of trips that are in my trips container, but what if I want to make a dashboard just to filter it with like what is the hottest destination that my users are traveling to, and that way I can add probably say more hotels or more restaurants particularly for that particular destination, so the users would have like more options for like with can they eat, what hotels they can stay at. Is there a way today that we can do that in Cosmos DB?
Yeah, so let's take a look at the design of our trips container and see why this query, this new dashboard, higher level query is so difficult to fulfill with our current architecture. So as our travel application is picking up steam and more users are using it, we have this need for cross-tenant queries. How many trips to Paris are next month? What is the top city? What is the top destination? These types of things are not really well served by our current architecture. Our current trips container is using a hierarchical partition key with tenant and then user and trip ID. This makes our agent queries really fast. An individual user can really quickly learn about all of their trips. But as the platform developer of our travel agent site, we want that higher level dashboard. We want to know how broadly across all tenants, how many trips to Paris are there next month? The issue with this query in our current architecture is that it's a cross-partition query. So Cosmos DB is a distributed database, and your data lives on multiple physical partitions. A query like this, where we're getting a count of all the trips to Paris, needs to be routed to every single physical partition so that we can count up all the trips and then give the answer back. For our new requirement of this dashboard broad across tenants, we need a new architecture. We can create a copy of our data using global secondary indexes. This allows us to create a secondary container, our global secondary index, that's partitioned on destination. This makes a query like finding all the trips to Paris extremely fast. We only need to check one partition instead of all of them in our previous container. Global secondary indexes are now generally available. They will automatically sync data from a source container and create a copy container with all of that synced data that's better suited for your query patterns. They really help you increase query efficiency and transform what would be very heavy cross-partition queries into single partition lookups. They help you isolate heavy workload operations into this secondary container to ensure that you can run them without impacting your transactional workload. So let's take a look at what this looks like in the Azure portal. I'm going to pull up my Azure Cosmos DB account, and I've got my trips container here. As you can see, I'm using a hierarchical partition key with tenant ID, user ID, and the trip. Now, this is a fairly heavy document. We've got this days array, which is storing all the information about the activities that the user is doing every day. Now, for my global secondary index, I don't actually need this low-level information about every trip. So when I define my global secondary index, which I've already created, my trips by destination, I can actually change the data model a little bit. I can project what properties are most important for me in this GSI. You see I have all of my trips here, but I've filtered out that days array. I don't need to have that written into my secondary data. I really can make sure the schema matches how I'm going to query it. Now, let's take a look at a query, and we'll run this same query, getting all the trips to Paris, France. First, I'm going to execute this on my trips container. So this is the primary container that we've already been using. And you can see I have 500 trips to France. If I look at the query stats, this cost me about 30 RUs. Now, imagine this query at scale when I'm constantly refreshing my dashboard and all my devs are looking at it. I wonder if there's a way that we can optimize this. So let's go into our GSI and let's go ahead and execute this same query. As I execute this same query against my GSI, I get the same answer, which is great. But if I look at the query stats, we see this time it only cost me 3 RUs. That's about a 90% savings. Now, the specific degree of savings will depend on your query and the physical partition layout of your source, but you can see how GSIs are a very powerful way to optimize your queries, especially when you have new evolving requirements. In this example, we didn't need a dashboard on day one. But global secondary indexes allowed us to add a GSI later on in the lifecycle of our application and ensure that our queries are still efficient even as our requirements evolve. So we covered a lot today, and I really want to bring it all together with some key takeaways to keep in mind. First, make sure that your agentic applications have durable memory and that they're scalable by design. Remember the different memory types that enable your agents to give better responses. You can ship even faster with an AI-native dev experience and the Azure Cosmos DB toolkit to analyze your application and ensure that you're using those best practices. Think about reliability and availability. Are there certain platform features you can take advantage of to avoid brittle error handling in your application code? Really thinking about mission-critical applications and how you can build ready-to-ship AI applications. I want to leave you with several resources today. This first link, that Cosmos DB Travel Multi-Agent, will be all of the demo code that we shared, including a workshop if you want to walk through building this application yourself. We've also got several links for some of the various announcements that we released today. Thank you so much, and I hope you enjoy the rest of Build.